November 24th, 2023, 12 a.m. EST. 500,000 people simultaneously hit buy now on the same sneaker drop. Every single one expects to check out in under 3 seconds. Your database has 5,000 connection slots. You need 25 million. Most platforms die here. They oversell inventory, charge users twice, then spend weeks issuing refunds. Shopify didn't die. They processed $4.2 million every single minute. That's not luck. That's 6 specific engineering decisions made years before Black Friday arrived. Let's put this in concrete terms. Shopify processed $9.3 billion in 24 hours on November 24, 2023. That's 61,000 orders every single minute at peak. Normal days see roughly 2,000 orders per minute, so this is a 30x traffic spike, sustained for hours. For context, most e-commerce infrastructure collapses at 5x. At 50 queries per order, Shopify's MySQL layer needed to handle over 50,000 queries per second. A single MySQL server maxes out at 100,000 QPS, and product page reads dwarf order writes by 100 to 1. This is the brutal physics of flash sales. Now here's where it gets interesting. How do you even begin to architect for this? Before the solutions, understand the failure modes. They hit in sequence, like dominoes. First, the thundering herd. 500,000 users arrive simultaneously. MySQL's connection pool holds 5,000 slots. The other 495,000 requests fail, then retry, making it worse. Second, inventory race conditions. 200 users buy the last sneaker simultaneously. All 200 read stock equals 1. All 200 proceed. Inventory hits -199. Third, duplicate orders. A user's request times out after 30 seconds. They click again. 2 charges, 2 orders, 1 furious customer. Fourth, hot partitions. 1 viral product sits on 1 database shard. That shard takes 100x load while all others idle. This is why engineers lose sleep before BFCM. Think of it like a theme park fast pass. You don't let 50,000 people charge the same ride simultaneously. You give them a ticket, tell them their wait time, and admit them in controlled batches. Shopify's queue works identically. When request rate to a product URL exceeds 5,000 requests per second, queue mode activates automatically. Each visitor receives a signed JWT containing their queue position and timestamp. That token lives in Redis. A background process then releases 500 tokens per second, exactly matching checkout backend capacity. Here's the critical detail. The queue runs at Fastly's CDN Edge. 499,500 of those 500,000 users never touch Shopify's application servers. The backend sees a flat 500 requests per second instead of a 500,000 request spike. Database connections stay under 20% utilization. 1 MySQL server, 5,000 connections, 100,000 queries per second maximum. Shopify needs 50,000 QPS just for orders, before product reads, which outnumber order writes 100 to 1. The answer is Vitess, originally built by YouTube in 2010, open-sourced in 2012. Shopify shards by shop ID. Every row, products, orders, inventory, customers, for a given merchant lives on the same shard. No cross-shard joins required. Shopify runs hundreds of MySQL shards. Each shard handles 500 to 1,000 shops. Vitess's VT-Gate proxy sits in front. Application code sends normal MySQL queries. VT-Gate routes them transparently. Each shard runs 1 primary plus 2 read replicas, tripling read throughput without changing a single line of application code. But here's the catch. Sharding alone doesn't solve the inventory race condition. This Lua script is the heart of Shopify's oversell prevention. Redis is single-threaded. Lua scripts execute atomically. No other command runs between lines. Here's what happens. The script reads current inventory. If it's 0 or less, it immediately returns -1, sold out. If stock exists, it atomically decrements by the requested quantity and sets a 10-minute TTL on a reservation key tied to the user's cart. The TTL is critical. If the user abandons checkout or payment fails, the reservation expires automatically. No cron job needed. Redis handles over 1 million operations per second at sub-millisecond latency. Compare that to MySQL row-level locking under 500,000 concurrent requests. That serializes everything. Redis doesn't lock at all. That's the entire point. A user on a 3G connection clicks place order. The request times out after 30 seconds. They panic and click again. Without idempotency, that's 2 payment charges and 2 orders. Shopify prevents this with a checkout token, a UUID v4 generated server-side when the checkout page loads. Every place order request carries this token as its idempotency key. Before calling Stripe, Shopify checks Redis. Has this key been processed in the last 24 hours? If yes, return the existing order result immediately. No second payment call. The key is also written to MySQL for 90-day audit retention. Stripe uses the exact same pattern on their end. Stripe's idempotency keys prevent duplicate charges even if Shopify's network drops after payment succeeds. 2 layers of duplicate prevention, 0 double charges. 80% of Shopify's BFCM traffic never reaches Shopify's servers. Fastly's CDN handles it entirely at the edge. Here's the caching strategy. Product page HTML, cached for exactly 10 seconds. Short TTL keeps pricing and inventory display fresh. Fastly serves 500,000 requests per second from cache. Shopify's origin only sees 50,000. Theme assets, CSS, JavaScript, images, are cached for 1 full year using content-addressed URLs. Storefront API GraphQL responses are cached by query hash for 5 seconds. What bypasses the CDN entirely? Cart operations, checkout pages containing PII, and order confirmations. The secret weapon is Fastly's surrogate key purging. When a merchant updates a price, Shopify sends one API call to Fastly. Every cached page referencing that product ID is invalidated globally within 150 milliseconds. In 2019, Shopify ran a single global monolith serving 1 million merchants. One bad database migration brought down every merchant simultaneously. That was the last time. Shopify restructured into pods, completely isolated self-contained stacks. Each pod owns a slice of merchants, sharded by shop ID range. Each pod has its own application servers, its own Vitess shard cluster, its own Redis cluster, its own job queue. If a viral merchant causes a memory spike in pod 7, pod 8 through pod 200 feel nothing. A bad deploy to pod 3 rolls back without touching pod 4. On BFCM 2023, Shopify can take an entire pod offline for emergency maintenance, and only a fraction of merchants are briefly affected. Think of it like circuit breakers in a building. One tripped breaker doesn't kill every floor. Shopify isn't alone in solving these problems. Amazon's Prime Day 2023 sold 375 million items in 48 hours, comparable BFCM scale load. Amazon uses ML-based predictive auto-scaling, models trained on historical traffic pre-warm EC2 instances 30 minutes before expected spikes. They don't wait for CloudWatch alarms. By then, it's too late. Stripe's idempotency keys are public API. Every charge request accepts an idempotency key, stored for 24 hours, preventing duplicate payment processing across any client. Discord faced a different spike problem, message fanout. When a celebrity posts in a 500,000 member server, Discord must deliver that message to 500,000 WebSocket connections simultaneously. Their solution, Cassandra-backed message queues with per-user delivery tracking. Different domain, identical thundering herd physics. Here's the production pattern for idempotent order creation. The checkout token is generated once when the checkout session starts. Every subsequent place order click sends the same token. On the server, we check Redis first, sub-millisecond lookup. If the order already exists, we return it immediately without touching the payment processor. If it's a new request, we call Stripe with the same token as Stripe's idempotency key. This guarantees that even if our network drops after Stripe charges the card but before we receive the response, a retry will return the existing charge, not create a new one. Finally, we persist to MySQL for audit. The entire hot path runs through Redis. MySQL only writes on first successful order creation. That's how Shopify handles millions of duplicate prevention checks per BFCM at under 1 millisecond each. The architecture is only half the story. Shopify's reliability on BFCM is won in October, not November. 6 weeks before Black Friday, Shopify runs synthetic load tests simulating 150% of projected peak traffic. Every pod is tested independently. Database query plans are reviewed manually. Slow queries get indexes or rewrites. Redis memory is pre-warmed with the full product catalog. Vitess shard hotspots are identified and pre-split before the day. The engineering team runs a BFCM simulation, a full dress rehearsal at scale. Merchants get a dedicated BFCM readiness checklist. Large merchants are proactively migrated to dedicated pods. On the day itself, Shopify runs a global war room with engineers on every time zone. Every pod has a dedicated on-call engineer. Incident response SLA is under 5 minutes. That operational rigor is what turns good architecture into 99.99% uptime. 6 engineering decisions made Shopify's Black Friday possible. 1. The flash sale queue runs at the CDN Edge. 499,500 of 500,000 users never touched the origin server. 2. Vitess shards MySQL by shop ID, hundreds of shards, each with 3 replicas, routing transparently through VTGate. 3. Redis Lua scripts provide atomic inventory reservation, no locks, no race conditions, 1 million operations per second. 4. Checkout tokens make every order creation idempotent. Duplicate clicks, network timeouts, and retries all return the same result. 5. Fastly Edge Caching absorbs 80% of traffic. 10-second TTL on product HTML, surrogate key purges in 150 milliseconds. 6. Pod architecture provides fault isolation. One viral merchant cannot take down a million others. Each concept independently solves a specific failure mode. Together they handle 30x traffic spikes without breaking a sweat. Shopify's BFCM architecture proves one thing. You don't survive 30x traffic spikes on the day. You survive them in the 6 weeks before. The next video breaks down how Discord handles 4 billion messages per day with Cassandra and Rust. If distributed systems at this scale interests you, subscribe and hit the bell. Every video drops a real system with real numbers.